In our examination of the causes of aircraft upsets, we'll start by examining the environmental factors. Now, this is the predominant cause of upsets, but unfortunately it's ironically the one over which we have the least control. Separate training focuses on weather and other environmental factors, so we won't labour it here, but the emphasis must be on the avoidance of high-risk situations. So in this section we'll focus on three things. We'll look at turbulence, wake turbulence, and aircraft icing. Firstly, turbulence. As we all well know, it's characterised by large variations in air current over a short distance, and it can lead to structural failure, extreme deviations in airspeed, altitude or attitude, and a momentary loss of control. Now, the main categories of turbulence that we'll consider are clear air turbulence, mountain wave, wind shear, thunderstorms, and microbursts. We'll cover these in summary only, and for more detailed training about weather, contact us and we'll put together a suitable training package. Firstly, let's look at clear air turbulence. Now, this is usually a high-level turbulence, which is normally above 15,000 feet above mean sea level. It's not associated with cumuliform clouds, including thunderstorms, so there may be no visual evidence that there is air turbulence ahead. It's often associated with jet streams, but can be very hard to predict. In general, areas of clear air turbulence are 100 to 300 miles long, elongated in the direction of the wind, 50 to 100 miles wide, 2,000 to 5,000 feet deep, and in terms of the time dimension may last between 30 minutes and a whole day. They are reportable and marked on high altitude weather maps, where they're classified in two main groups, moderate or severe, with the symbology for each of these classifications denoted in the top right corner of these boxes. The conditions which lead to the classification as moderate or severe are listed here, but suffice to say that clear air turbulence is something which should be avoided and treated with a great deal of respect. Moving on to mountain wave, this is caused by the mechanical turbulence of air passing over mountainous areas. Airflow, which is passing over the mountains, will be forced to rise, and as it does so, in certain conditions this can set off a wave effect which occurs for many miles past the downwind end of the mountain range. One of the indicators that mountain wave is present are the very peculiar lenticular clouds which can sit above a mountain, as denoted in the picture here, and also can occur at the areas of the rising air in bands downwind of the mountain range. They've often been described as looking like spaceships and have a very distinctive look to them. One of the indicators of particular danger associated with mountain range are the rotor clouds, which tend to occur lower down and form by a drop in pressure caused by rotating airflows towards the lower portions of the mountain wave. But note that the clouds are not a reliable indicator and may not always be present. So what is it that leads to the formation of mountain wave? Well, some of the key risk factors are wind speeds above 50 knots at the peaks of mountains, winds near perpendicular to a ridgeline, in or near cumuliform clouds or thunderstorms, and within 50 to 100 miles on the cold side of the centre of a jet stream. They are sometimes associated with troughs aloft or lows aloft where the wind shear is greater than or equal to 10 knots per 1,000 feet and or 40 knots of horizontal wind shear per 150 nautical miles. One of the key things to remember with mountain wave is it can be extremely turbulent, and there's a very high risk in and below the level of well-developed rotor clouds. So wind shear. We've talked a little bit about wind shear in the previous couple of examples of environmental causes of upsets, but wind shear in this setting is the wind variation at low altitude. It's particularly a hazard during takeoff and approach when the aircraft is low to the ground and in a vulnerable low speed condition. Wind shear can result from a wide variety of conditions, including topographical conditions, temperature inversions, sea breezes, frontal systems, or strong surface winds. It can also be associated with thunderstorms and rain showers, which we'll discuss in a little bit more detail. And so to thunderstorms. Thunderstorms can be mainly classified into two groups. Air mass thunderstorms are randomly distributed, caused by a large unstable air mass sat over the ground being heated from below. Frontal thunderstorms, however, are generally spread along squall lines and are a result of one air mass being forced up over another at a front. Taking the first of these then, the air mass thunderstorms, the biggest risk to us is that they can cause localized gust fronts due to downdrafts. If we look at the life cycle of these air mass thunderstorms, we can see that localized surface heating is the initial cause, and the rising air, as it cools, forms cumulus clouds. As this air is continually forced up due to the continued localized surface heating, the cloud builds, and the air that is being forced up into the higher altitudes is rapidly cooled and so starts to sink. As this sinking air comes back down to Earth, we get the formation of gust fronts, with air being forced out in all directions as it reaches the surface, and heavy rain. As this storm builds, the rain actually cuts off the hot air which is rising to form the storm, and the storm starts to dissipate. So therefore, these air mass thunderstorms are typically of a short life cycle and usually last less than an hour. But the gust fronts that they can cause are normally very turbulent. So the biggest risk to us is during takeoff and landing. Moving on to frontal systems, thunderstorms can generate heavy rain, hail, and gusty winds, and in some parts of the world, possibly tornadoes. The effect that this has is that large changes in horizontal wind speed and direction may be present throughout a very small altitude change. Now, unlike the air mass thunderstorm, which are reasonably vertical in their extent, frontal thunderstorms, by the nature of the way they are formed, tend to be slightly angled due to the wind changes, and this allows the rain to fall away from the hot air updrafts which are forming the thunderstorm. The result of this is that the storm and the downdrafts are allowed to build in intensity and last for several hours. So areas of downdrafts can be as far as 1 to 5 miles in diameter. Additionally, the changes in horizontal wind speed and direction through the whole range of altitudes can lead to very significant wind shear and turbulence, not just at low level, but through a larger altitude band. Microbursts, often associated with thunderstorms, are concentrated, more severe downdrafts associated with convective weather. They are associated with approximately 5% of all thunderstorms, so 1 in 20, and cause downdrafts typically of only a few hundred to 3,000 feet across. During a microburst, the surface winds intensify for around 5 minutes after the downdraft first hits, and typically dissipate around 10 to 20 minutes later. Here we have in this diagram a symmetrical microburst where air descending from the developed convective cloud is forced down to the surface and flows outwards evenly to one side and the other. For an aircraft transiting this microburst, they will see an increase in indicated airspeed followed by a rapid decrease as they go out of the other side. Microburst outflows are not always symmetrical, and therefore the speed gain may not be noticed, or may be less than the speed loss on exiting the microburst. And beware, because it's vital to recognize that some microbursts cannot be successfully escaped with any known technique. The emphasis therefore needs to be on the avoidance of microbursts. Moving on from turbulence, we said that the next category we'd look at was wake turbulence. As we saw at the start with the statistics from NASA, Wake turbulence is the leading cause of environmentally induced upsets. So how are they formed? We talked about induced drag and how vortices were caused by a pressure differential between the top and the bottom wing surfaces at the wingtip. Now these vortices and their magnitude are primarily affected by the weight of the aircraft, the wingspan, the speed, and are at their worst between large, heavy aircraft at high angles of attack. Typically, we come across this as large aircraft are taking off or landing. The effects on us are severe sudden rolling and or pitching movements, and are at their worst for aircraft with small wingspan, where the wingspan of the aircraft affected fits within a single vortex from the preceding aircraft. Notable if you're a business jet operator. To avoid wake turbulence, we need to know where it is. The wake turbulence tends to level off within approximately 5 nautical miles of most aeroplanes and around 500 to 900 feet below the flight path of the preceding aeroplane. So we need to make sure that we remain at or above the flight path of the preceding aircraft and maintain a minimum of 1,000 feet vertical separation when crossing beneath. Most of the time, of course, with time-based separation, air traffic control are working to avoid a situation where wake turbulence can occur. However, it is for you as the pilot to be thinking about the effects on your airplane and how to avoid it. Our final section, having covered turbulence, wake turbulence, is now to move on to aircraft icing. The most significant part of aircraft icing is due to a performance degradation as a result of ice accumulation. Now, large degradation of aircraft performance is possible from the surface roughness of only a small amount of contamination and will vary with the location of the ice accumulation and the roughness of its surface, and produce unexpected handling characteristics which can be unpredictable. The effects, therefore, could be a reduction in the maximum lift capability of our aircraft, an increase in drag, and unanticipated changes in the stability and control of the aircraft. So, need to work to remove the effect of ice as quickly as possible. So, in this brief, we've looked at turbulence, wake turbulence, and aircraft icing. These three are the primary categories of environmental causes of aircraft upsets.